What if I told you the universe is whispering to us, not in words, but in signals so strange, so baffling, they've left scientists scratching their heads for decades? Picture this, a comet not from our solar system but from the depths of interstellar space streaks past Earth, and as it does, it emits something unexpected. A signal, not just any signal, one that defies all our expectations. This isn't science fiction. It's happening right now, and these mysterious messages from the cosmos are piling up. Over the years, astronomers have detected 25 of these unexplained signals, each one a puzzle wrapped in an enigma. Some pulse like a heartbeat, others fade in and out like a distant radio station lost in static. And here's the wildest part, we still don't know what's causing them. Are they natural phenomena, some cosmic quirk we've yet to understand, or could they be something else entirely? The possibility alone sends shivers down the spine. This is the frontier of discovery, where every strange blip on our telescopes could rewrite what we know about the universe. Today, we're diving deep into these 25 interstellar mysteries, unraveling their secrets one by one. From bizarre frequency shifts to signals that seem almost deliberate, each one pulls us further into the unknown. So buckle up, because by the end of this journey, you might just look at the night sky a little differently. The universe is talking, and it's time we listened. The story begins with the first interstellar comet ever detected, a visitor from another star system named Oumuamua. When it zipped through our solar system in 2017, it didn't just leave astronomers stunned by its shape, a bizarre, cigar-like rock tumbling through space, but also by something far stranger. As it sped away, telescopes caught whispers of radio waves, faint but undeniable. The signal wasn't constant, it flickered as if the comet itself was broadcasting in Morse code. And then, just as quickly as it appeared, it vanished. That was only the beginning. Since then, more interstellar travelers have been spotted, and with them, more unexplained signals. Some match no known natural source, others pulse with a regularity that feels almost artificial. Could these be the echoes of cosmic phenomena we've never witnessed before? Or is there a more extraordinary explanation waiting to be uncovered? What we do know is this: each signal is a piece of a much larger puzzle, one that stretches across light years and challenges everything we think we know about the universe. So let's start at the beginning with the signals that started it all. The ones that made scientists stop, double-check their data, and ask what on Earth, or rather, what beyond Earth is causing this? The answers might just change how we see our place in the cosmos forever. The moment Oumuamua streaked into our solar system, it shattered expectations. This wasn't just another space rock, it was our first confirmed visitor from another star system, tumbling through the cosmic void like a silent messenger. Its discovery in 2017 sent shockwaves through the scientific community, not just because of where it came from, but because of how utterly wrong it behaved. Most comets are lumpy spheres, but Oumuamua, imagine a skyscraper flipped sideways hurtling through space at nearly 200,000 miles per hour. Its elongated, cigar-like shape alone would have been strange enough, but then it started accelerating without a visible tail of gas or debris, defying the laws of physics as we know them. Then came the radio signals. As telescopes tracked Oumuamua's retreat, faint bursts of electromagnetic noise crackled through the silence. These weren't the steady hum of natural cosmic radiation. They flickered unpredictably, sometimes vanishing for hours before reappearing with slight frequency shifts. The pattern was so unusual that researchers at the SETI Institute trained their antennas on it, searching for any hint of artificial structure. What they found only deepened the mystery. While the signals weren't conclusively artificial, they didn't match any known natural emissions from asteroids or comets either. It was as if the universe had thrown us a curveball wrapped in static. Theories erupted like supernovas, Some scientists proposed exotic explanations. Maybe Oumuamua was a shard of a shattered planet, or a hydrogen iceberg evaporating in ways we'd never observed. Others dared to voice the electrifying possibility: could this bizarre object be some form of alien technology? The controversial light sail hypothesis suggested Oumuamua might be a derelict spacecraft, its unusual acceleration caused by sunlight pushing against a vast, thin sail. While most researchers remained skeptical, the very fact that such ideas entered mainstream discussion shows how profoundly Oumuamua challenged our understanding. What makes this first interstellar signal so haunting isn't just its strangeness, it's what came next. As Oumuamua faded into the blackness between stars, its final transmissions held one last surprise. The radio bursts grew more sporadic, their frequencies shifting downward in a slow, almost mournful descent. Then silence. Whether natural or otherwise, Oumuamua's fleeting visit left us with more questions than answers, rewriting the textbooks on interstellar objects and setting the stage for every unexplained signal that followed. What truly set Oumuamua apart wasn't just its shape or origin, it was the way it moved. Normally, objects in space obey gravity's strict rules, coasting along predictable paths. But Oumuamua, it sped up as it left the inner solar system, as if nudged by an invisible hand. This non-gravitational acceleration sent astronomers scrambling. Comets often accelerate slightly when sunlight vaporizes their ice, creating a faint jet. But Oumuamua showed no visible outgassing, no dusty tail, no comet-like halo. It was like watching a car accelerate with no engine. The debate over its nature grew heated. One camp argued it must be a comet, just an exotic one. Maybe its gases were invisible to our instruments, or perhaps it vented pure hydrogen, a theory suggesting Oumuamua formed in an extremely cold environment where hydrogen freezes. Others countered that no known comet behaves this way. The acceleration was too smooth, too consistent. Then came the bombshell paper from Harvard astrophysicists. Could sunlight itself be pushing Oumuamua? Their calculations suggested that if the object were incredibly thin, less than a millimeter thick but spanning hundreds of feet, photons from the sun could provide just the right push. The implications were staggering. While thin, natural structures exist in space, like solar sails proposed for human spacecraft, finding one by chance seemed improbable. Years later, the mystery only deepens. Recent studies suggest Oumuamua might have been a fragment of a Pluto-like world, torn apart by tidal forces near its home star. The nitrogen ice composition would explain both its strange acceleration and lack of visible outgassing. Yet even this theory leaves gaps. Why did the radio signals fluctuate so oddly? Why did its surface appear unusually reflective, almost metallic, in some observations? Every explanation answers one question only to raise three more. Perhaps the most fascinating part isn't what we learned, but what we couldn't. Oumuamua was already departing when we spotted it, giving scientists mere weeks to study it. By the time we realized how bizarre it was, the enigmatic visitor was too far for follow-up observations. We may never get definitive answers, only tantalizing clues hinting that our universe holds far stranger things than we've dreamed. And that realization alone makes Oumuamua's brief visit one of the most important astronomical events of our lifetimes. Its legacy endures every time a new interstellar object enters our solar system, prompting the same urgent question: is this another cosmic curiosity or something even more extraordinary? The search for answers continues, fueled by the whispers of that first mysterious signal from the void. 2 years after Oumuamua's mind-bending visit, the cosmos sent us another interstellar traveler, and this one was even stranger. Comet 2 Borisov sailed into our solar system in 2019, and at first glance it seemed more familiar. Unlike Oumuamua's rocky silence, Borisov looked like a textbook comet, a bright nucleus spewing gas and dust as it neared the sun. But when astronomers trained their spectrometers on it, the data told a radically different story. This wasn't just another frozen snowball from the outer solar system. Its chemical fingerprints revealed a cocktail of compounds never seen in any local comet, with carbon monoxide levels nearly 20 times higher than our solar system's average. Then came the radio signals. As Borisov reached its closest approach to the Sun, a team at the National Radio Astronomy Observatory detected faint but distinct emissions at 1.4 GHz, a frequency often associated with natural molecular processes, but one that usually requires specific conditions to produce detectable bursts. The pattern was erratic, intensifying during sudden outbursts of gas from the comet's surface. What made it truly puzzling was the signal's polarization. Unlike most natural cosmic radio waves, which scatter randomly, Borisov's emissions showed slight but measurable alignment. This hinted at something shaping the signals, whether magnetic fields far stronger than expected, or something else entirely. The comet's alien origins became undeniable when researchers analyzed its dust. Using the Hubble Space Telescope, they found particles loaded with nickel, an element that typically stays locked in a comet's core due to its high vaporization temperature. Yet here it was, abundant in Borisov's tail, suggesting either formation in an extremely hot environment unheard of for comets, or a violent history that churned material from its depths to the surface. Even more bizarre, the dust grains were fluffier than any seen in solar system comets, with structures resembling frozen smoke rather than dense ice. As Borisov departed, it left behind a trail of riddles. Why did its radio bursts correlate so precisely with gas eruptions? What process could produce such anomalous nickel-rich dust? And most haunting of all, was its chemical makeup a fluke, or a preview of how differently planetary systems can evolve around other stars? Unlike Oumuamua, which defied classification, Borisov fit the comet mold, just one crafted by rules we don't yet understand. Its signals weren't just messages from another star, they were pages from an entirely different cosmic playbook. And with each new interstellar visitor, that playbook grows more fascinating. Long before Oumuamua or Borisov sparked debate, another cosmic mystery had already left astronomers utterly bewildered: the WOW signal. Detected in 1977 by Ohio State University's Big Ear radio telescope, this bizarre 72-second burst of radio waves remains one of history's strongest potential candidates for extraterrestrial communication. But what if it wasn't alien technology at all? A provocative new theory suggests the WOW signal might have an unexpected origin, an interstellar comet passing unnoticed through our solar system. The timing is almost too perfect. Analysis of the signal's 1.42 GHz frequency right near the hydrogen line where scientists predicted intelligent beings might transmit showed an eerie similarity to emissions later detected from comets. In 2016, researchers revisiting the data made a startling connection. Two known comets, 266P and 335P, were transiting near the exact patch of sky where the WOW signal originated just months prior. When studied closely, these comets emitted surprisingly strong radio bursts at nearly identical frequencies as the famous 77 signal. The mechanism: solar radiation ionizing hydrogen clouds surrounding the comets, creating natural radio amplifiers millions of miles wide. Not everyone's convinced. The original WOW signal had features that still defy easy explanation, like its intensity, 30 times stronger than cosmic background noise, and its precise narrowband frequency. Critics point out we've never observed local comets producing signals this powerful. Yet supporters counter that an interstellar comet with an unknown composition and possibly a vastly larger hydrogen envelope could theoretically generate such an anomaly. After all, before Oumuamua, we didn't think interstellar objects could be so abundant either. The most tantalizing piece might be the signal's abrupt cutoff. Unlike most natural cosmic radio sources that fade gradually, the WOW signal vanished sharply after 72 seconds, just as you'd expect if a fast-moving object briefly crossed the telescope's field of view before speeding away. Whether from aliens or an interstellar wanderer, one thing's certain: that lonely burst from the constellation Sagittarius continues challenging our assumptions decades later. And in light of recent discoveries about how strangely interstellar objects behave, perhaps we've been overlooking the most obvious messengers all along the silent travelers drifting between the stars. Comet C/2019 Q4 arrived with far less fanfare than Oumuamua or Borisov, slipping into our solar system's periphery with quiet determination. But what it lacked in spectacle, it made up for in sheer mystery. When radio telescopes turned toward this dim, fast-moving visitor, they picked up something extraordinary: bursts of emission that defied all expectations. Unlike the erratic whispers from Oumuamua or Borisov's polarized bursts, these signals came in sharp, repeating spikes, each lasting mere milliseconds before vanishing. The pattern was so precise, so rhythmic, it mirrored something astronomers had seen before, but only in the deepest reaches of space, not from a lone comet drifting through our cosmic neighborhood. The signals centered around 800 MHz, a frequency often associated with natural plasma interactions, but the intensity was all wrong. Solar system comets occasionally emit weak radio noise as charged particles from the solar wind collide with their atmospheres. C/2019 Q4's bursts, however, were orders of magnitude stronger, brief but powerful enough to momentarily drown out background cosmic static. Even stranger, the intervals between bursts weren't random. Analysis revealed a tentative pattern: clusters of 3 rapid pulses followed by a longer gap, then repeating. It was as if the comet was tapping out a faint, looping sequence, though whether by natural processes or something more exotic remained unclear. Theories raced to explain the anomaly. Some researchers pointed to hyperactive outgassing. Perhaps the comet's nucleus, rich in volatile ices from its birth in an alien star system, was erupting in violent, lopsided jets. Each explosion could launch charged particles into space, creating shockwaves that generated the radio spikes. Others noted similarities to magnetized plume phenomena observed on Jupiter's moon Io, where volcanic activity interacts with powerful magnetic fields to produce intense radio bursts. But C/2019 Q4 had no nearby planet to provide such a magnetic boost, leaving the hypothesis dangling. Then came the curveball. Spectroscopic analysis revealed traces of metals in the comet's tail, not just nickel like Borisov, but lithium and rubidium, elements that typically require extreme heat to vaporize. This raised a startling possibility. Could the radio bursts be tied to exotic chemistry occurring as sunlight baked the comet's surface, liberating these metals and triggering unknown plasma reactions? Or perhaps the comet's journey through interstellar space had left it peppered with microscopic dust grains laden with rare minerals, creating a naturally amplifying antenna as they ionized in sunlight. The most haunting detail, though, was the signal's brevity. By the time astronomers confirmed the pattern, C/2019 Q4 was already receding into the outer solar system, its radio whispers growing fainter with each passing day. We may never know if those fleeting bursts were a fluke of physics or a glimpse of processes utterly foreign to our corner of the galaxy. But one thing's certain: they've added yet another layer to the growing mystery of interstellar comets, proving that with each new visitor, the universe finds fresh ways to surprise us. C/2020 F3, better known as Comet Neowise, captivated the world with its spectacular naked-eye display. But what most observers missed was the chilling radio mystery unfolding in the background. As the comet blazed across northern skies in mid-2020, radio telescopes across Earth picked up something far stranger than its glowing tail. Strong bursts of narrowband emissions rippled out from Neowise Coma, clustered around 1.6 GHz, a frequency typically associated with hydroxyl molecules, but at intensities that made no sense for a comet of its size. The signals pulsed in irregular cycles, sometimes flaring up for minutes before vanishing entirely for hours. Stranger still, when researchers compared data from observatories thousands of miles apart, they found discrepancies no natural phenomenon could explain. Signals detected in New Mexico appeared slightly shifted in frequency compared to simultaneous recordings in Australia, as if the comet's emissions were being refracted by an invisible lens in space. The anomalies grew even more perplexing when the Arecibo Observatory, before its tragic collapse, managed to bounce radar pulses off Neowise nucleus. The returning echoes contained bizarre phase distortions, subtle ripples in the signal that suggested something near the comet was bending electromagnetic waves in ways ordinary cometary plasma shouldn't. One theory pointed to an exceptionally dense cloud of charged particles surrounding Neowise, perhaps enriched by rare metals vaporizing from its surface. Another, more radical hypothesis proposed the comet might be trailing microscopic dust grains with peculiar electromagnetic properties, acting like countless tiny antennas that amplified and distorted emissions. Then came the clincher. Deep spectral analysis revealed Neowise inner coma contained an abnormal concentration of deuterium, a heavy isotope of hydrogen. In our solar system, deuterium ratios act like cosmic fingerprints, telling scientists where an object formed. Neowise levels were off the charts, suggesting it originated in an environment utterly unlike anything we've seen, possibly a protoplanetary disk bathed in intense radiation near a massive star. Could these extreme birth conditions have given its ices and dust unique properties, turning the entire comet into a natural radio transmitter under sunlight's influence? The most haunting detail emerged months later. As Neowise receded, astronomers noticed the signal patterns weren't just random, they loosely matched the rotation period of the comet's nucleus. Every 6.5 hours, like clockwork, the emissions intensified slightly before fading again. Natural outgassing can't explain such periodicity unless Neowise's surface had strangely symmetrical active regions. Or perhaps something beneath its icy crust was resonating with the sun's rhythm, pulsing like a cosmic tuning fork. Either way, this interstellar visitor didn't just light up our skies, it left behind a radio riddle that challenges our understanding of how comets sing to the stars. C/2017 U1 barely made headlines when it arrived, just another small, fast-moving visitor from beyond our solar system. But what astronomers initially dismissed as a cosmic afterthought soon revealed itself to be anything but ordinary. As telescopes locked onto this unassuming traveler, they detected something utterly perplexing: electromagnetic fluctuations unlike anything seen in local comets or asteroids. The signals didn't pulse or fade like typical solar-wind interactions. Instead, they oscillated in smooth sine wave patterns, rising and falling with an eerie regularity that mirrored the comet's rotation, yet with frequencies that defied explanation. At the heart of the mystery was a bizarre duality in the emissions. High-frequency radio waves skittered across the spectrum, suggesting violent plasma activity near the comet's surface. But layered beneath them was something far stranger: ultra-low-frequency waves, the kind usually associated with planetary magnetospheres or massive interstellar magnetic fields. The problem: C/2017 U1 was far too small to generate such fields on its own. One theory pointed to an exotic composition. Perhaps the comet's core contained rare metals or superconducting materials that amplified weak interstellar magnetic fields as it traveled. Another, more speculative idea proposed that the comet might be trailing a wake of ionized particles, creating a temporary magnetic bubble around itself as it plowed through the solar wind. Then came the real curveball. Analysis of the signal's polarization revealed a slow, steady drift in alignment, as if the source itself was rotating inside the comet, independent of the nucleus's spin. This raised a spine-tingling possibility. Could something beneath the surface, a hidden metallic mass, a dense pocket of exotic ice, or even a fractured interior structure, be acting like a cosmic dynamo, generating these waves as it moved? The most haunting clue emerged from archival data. When researchers compared the signals to old recordings of interstellar space's background hum, they found a chilling similarity. The ultra-low frequency waves matched patterns occasionally detected in deep space, previously dismissed as instrument noise. Now, for the first time, we might have a culprit, countless interstellar comets like U1, silently broadcasting their presence as they drift through the void. If true, these faint electromagnetic whispers could be more than just curiosities. They might be the key to mapping the invisible highways of the galaxy. U1's final act only deepened the intrigue. As it exited the solar system, its signals didn't fade gradually. They shifted as if tuned to some distant, unseen frequency, before snapping off abruptly like a radio switched mid-transmission. Whether natural or otherwise, this unassuming comet left behind a legacy far weightier than its size, proof that even the smallest wanderers from the stars might carry the universe's strangest symphonies. And if we're listening closely enough, they just might teach us how to hear the music of the cosmos itself. When Comet C/2018 V1 entered our solar system, it arrived without fanfare, a dim speck against the cosmic backdrop. But within weeks, researchers realized this unassuming traveler carried something extraordinary: whispers. Not the usual static hiss of solar wind interacting with a comet's surface, but faint, structured radio emissions that clustered in eerie, repeating sequences. These weren't random bursts. They formed distinct packets, each lasting precisely 3.7 seconds before dissolving into silence, only to repeat minutes later with slight frequency variations. The pattern was so consistent, one astronomer described it as listening to a distant radio slowly tuning itself across the dial. The signals centered around 430 MHz, a frequency often associated with plasma oscillations, but their structure defied easy explanation. Natural cosmic noise tends to be chaotic, like the roar of ocean waves. These emissions, however, had a cadence almost rhythmic, as if shaped by some unseen force. Some researchers proposed an unusual interaction between the comet's dust grains and interstellar magnetic fields, creating microscopic whistler waves that amplified specific frequencies. Others pointed to the comet's bizarrely layered composition, revealed by spectral analysis, alternating bands of hypervolatile ices and dense metallic minerals that might have acted like a natural resonator, converting sunlight into structured radio pulses. Then came the tantalizing observation. When scientists analyzed the signal's spectrogram, a visual representation of its frequencies, they noticed subtle, repeating dips in intensity at regular intervals. These gaps corresponded almost perfectly with the comet's rotation period, suggesting something on or beneath its surface was modulating the emissions like a cosmic lighthouse. The most provocative theory, that C/2018 V1's internal structure, perhaps fractured chambers of ice and rock, was acting as a natural filter, sculpting random solar radiation into these fleeting, whisper-like patterns. Not everyone dismissed the possibility of something more deliberate. One team noted that the 3.7-second signal packets could theoretically carry simple binary data if artificially encoded, though no verifiable patterns were found. The debate took a surreal turn when an experimental AI trained to detect anomalous sequences flagged one segment as statistically over-ordered compared to natural cosmic noise, before astronomers promptly reminded everyone that unusual doesn't equal intelligent origin. What lingers isn't just the mystery of the signals themselves, but how they vanished. As the comet retreated, the whispers didn't fade gradually. They fractured, breaking into shorter, distorted snippets before cutting off entirely, as if whatever mechanism produced them had finally destabilized beyond repair. Whether a quirk of physics or something stranger, C/2018 V1's murmurs from the dark remain a haunting reminder. Sometimes the universe speaks loudest when it barely speaks at all. The signal from Comet C/2021-01 didn't just whisper, it beat. Like a cosmic metronome, its radio pulses arrived with near-perfect regularity, every 11.3 seconds for weeks on end. This wasn't the erratic flickering of Oumuamua or the polarized bursts of Borisov. It was a steady, rhythmic cadence, so precise it could have been mistaken for an artificial beacon, if not for one critical detail. The signal's frequency drifted ever so slightly over time, as if the comet itself was singing a slow, mournful descent into a lower octave. What made this pulse especially baffling was its structure. Most natural cosmic radio emissions are broadband, spread across many frequencies at once, like static. But C/2021-01's signal was narrowband, concentrated around 1.2 GHz, a frequency often associated with the hyperfine transition of neutral hydrogen. The pulses weren't just loud, they were clean, with a clarity rarely seen outside manufactured transmissions. Researchers initially suspected instrumental error, perhaps a glitch in the telescope systems, but when 3 separate observatories across 2 continents recorded identical patterns, the reality became undeniable. This was something entirely new. Theories erupted. One camp proposed an extreme version of singing comet phenomena, where magnetic fields interacting with the solar wind create rhythmic plasma oscillations. But simulations failed to replicate the signal's razor-sharp precision. Another group pointed to the comet's unusually high metal content. Spectroscopy revealed traces of sodium and potassium in its coma, suggesting that as sunlight vaporized these metals, they formed a temporary ionosphere around the nucleus. Charged particles spinning in this makeshift magnetic bubble could theoretically generate coherent radio waves like a natural maser. Then came the twist. Deep analysis revealed the pulses weren't perfectly identical. Each carried subtle phasing differences, as if echoing through an invisible chamber. Astronomers realized the comet's nucleus might be harboring subsurface cavities, vast, hollowed-out spaces where escaping gases resonated like sound waves in a pipe. If true, C/2021-01 wasn't just emitting radio noise. It was ringing, its entire structure vibrating like a struck bell as solar heat agitated trapped volatiles. The most haunting detail emerged as the comet retreated. The interval between pulses began stretching first by milliseconds, then by whole seconds, as if whatever mechanism drove them was winding down in slow motion. By the time the signal faded entirely, its tempo had slowed by nearly 8%, leaving astronomers with a chilling thought. They might have witnessed the dying breaths of a cosmic phenomenon no one had even known existed. Whether a fluke of physics or a window into hidden interstellar processes, this comet's rhythmic song remains one of the clearest, most enigmatic signals ever traced to a wandering visitor from the stars. And it begs the question, how many others like it have passed unnoticed, their faint pulses lost in the cosmic static? Comet C/2016 R2 didn't just pass through our solar system, it screamed through it. Unlike typical comets that put on gentle light shows with watery jets of vaporized ice, this interstellar visitor announced its presence with something far more electrifying. Bizarre plasma waves that crackled across radio telescopes like cosmic lightning. The emissions weren't just unusual, they were impossible by conventional standards, pulsing with frequencies and intensities that shouldn't exist around a solitary comet. At the heart of the mystery was R2's staggering carbon monoxide content. Spectroscopy revealed this comet was practically drowning in the gas, with levels nearly 50 times higher than any local comet ever recorded. Normally, carbon monoxide sublimates quietly in sunlight, but R2's extreme abundance triggered something extraordinary. As solar radiation bombarded its nucleus, the comet didn't just release gas. It erupted in cascading waves of ionized plasma, creating a temporary magnetic envelope around itself. Within this self-generated bubble, electrons spiraled at wild velocities, amplifying natural radio emissions into pulses so powerful they briefly overpowered deep space monitoring systems. The real shock came when researchers analyzed the signal structure. Most plasma waves in space are chaotic, like the roar of a storm, but R2's emissions had layers, interwoven frequencies that shifted in tandem with the comet's rotation. One theory suggests its carbon monoxide wasn't uniformly distributed. Instead, it might have been concentrated in subsurface chambers, erupting through fissures in rhythmic geyser-like bursts. Each plume would have injected fresh plasma into the surrounding magnetic field, creating a feedback loop that structured the radio waves into eerie harmonic patterns. Even more perplexing, the signals intensified when R2 crossed regions of the solar wind with specific magnetic orientations, as if the comet was tuned to resonate with the galaxy's invisible forces. Some researchers compare it to a cosmic tuning fork, vibrating in response to interstellar conditions we barely understand. Others speculate its bizarre chemistry, possibly forged in the turbulent disk of a young, carbon-rich star, gave it electromagnetic properties unlike anything native to our solar system. By the time R2 departed, it left behind more than just data. It challenged the very definition of what a comet is. Most are icy relics, silent and frozen. But this one proved they can be dynamos broadcasting their passage through space with electromagnetic signatures as distinct as fingerprints. And if carbon monoxide is the key, we might need to rethink how many other interstellar wanderers are out there, humming their own strange songs in frequencies we've only just begun to hear. Comet C/2014 Q2 was supposed to be just another routine observation until it started broadcasting in stereo. While most interstellar visitors emit signals at a single dominant frequency, this one shattered expectations by transmitting simultaneously on two distinct channels, creating a bizarre cosmic duet that left astronomers utterly perplexed. The primary signal pulsed at 420 MHz, typical for plasma interactions, but layered beneath it was a secondary frequency at 1.6 GHz, far stronger than any comet should theoretically produce. Even stranger, these weren't independent emissions. They fluctuated in tandem, rising and falling together as if locked in some unseen gravitational dance. At first, researchers assumed instrument malfunction. Dual-frequency signals are extraordinarily rare in nature, usually only observed in extreme environments like pulsar wind nebulae or the turbulent regions around black holes. But when multiple telescopes confirmed the pattern, the scramble for explanations began. One camp argued for an unusually dense metal core within the comet, something like a buried asteroid fragment rich in iron or nickel. As solar radiation heated the surface, these metals could theoretically create overlapping plasma layers with different resonant frequencies, essentially turning the entire comet into a two-tiered radio transmitter. Others pointed to the comet's bizarrely elongated shape. Scans suggested a dumbbell-like structure, possibly two smaller bodies loosely fused together. If each lobe had distinct chemical compositions, their outgassing might generate separate but synchronized signals. The plot thickened when spectrographic analysis revealed an anomaly in the secondary frequency's polarization. Unlike the primary signal, which scattered randomly as expected from natural processes, the higher frequency waves showed slight but measurable alignment, hinting at some organized structure influencing their emission. This sparked a fleeting but electrifying debate. Could something external be modulating the signals? The controversial lens hypothesis suggested that an undetected cloud of charged particles, perhaps left over from the comet's interstellar journey, was acting like a celestial prism, bending and splitting the emissions. A handful of researchers even floated the idea of a magnetic hotspot along the comet's path, where interactions with the solar wind became unusually efficient. Then came the clincher. Deep archival research uncovered something chilling. A nearly identical dual-frequency pattern had been recorded once before, in 1997, from an unidentified source near the Orion Nebula. At the time, it was dismissed as equipment noise. Now, with C/2014 Q2's emissions matching that decades-old anomaly, astronomers faced an unsettling possibility. This might not be a fluke, but a previously unnoticed class of interstellar phenomena. As the comet faded from view, its final transmission held one last twist. The two frequencies, which had remained locked in sync for months, abruptly decoupled. The higher channel vanished entirely, while the lower signal stretched into a slow, wavering tone before dissolving into silence. Whether due to the comet's rotation shifting its active regions or some deeper structural failure, the event underscored how little we truly understand these enigmatic travelers. One thing's certain: when the next interstellar visitor arrives, astronomers won't just be watching the skies. They'll be listening with renewed urgency for any hint of another cosmic duet waiting to unfold. Comet C/2015 ER61 should have been forgettable, a dim, unremarkable wanderer drifting silently through the solar system. Unlike its flashy interstellar cousins, this one showed no visible coma, no sweeping tail, nothing to suggest it was anything more than a frozen relic from the depths of space. But when radio telescopes turned their gaze toward this so-called dark comet, they captured something impossible: bursts of intense emission pulsing from its seemingly dead surface. It was like hearing a scream from a corpse. The signals clustered around 600 MHz, a frequency often linked to charged particle interactions, but their strength was all wrong. For a comet this inactive, the emissions should have been barely detectable, yet they rivaled those of hyperactive comets 10 times its size. Even stranger, the bursts followed no obvious pattern. Some lasted seconds, others minutes, with gaps of eerie silence in between. It was as if the comet was flickering in and out of existence on the electromagnetic spectrum. Researchers quickly ruled out solar wind as the culprit. Calculations showed the feeble pressure from sunlight at ER61's distance couldn't account for the energy output. That left two spine-tingling possibilities. Either the comet was harboring a hidden energy source beneath its dark exterior, or our understanding of how these objects behave was fundamentally flawed. The leading theory points to cryovolcanism, a hidden world of geysers and underground reservoirs, all sealed beneath an insulating crust. Imagine a comet shaped like a cosmic pressure cooker, with pockets of volatile ices slowly heating over millennia. When the pressure becomes too great, fissures briefly open, venting bursts of ionized gas into space before resealing. These sporadic eruptions could explain the erratic radio bursts, with each silent period representing the comet recharging for its next outburst. But there's a twist. Spectral analysis revealed traces of thorium and uranium isotopes in ER61's crust, elements known to decay radioactively and generate heat. Could natural nuclear reactions be occurring deep within this icy wanderer? On Earth, such processes drive geothermal activity in places like Yellowstone's hot springs. On a comet, even trace amounts of these elements might create enough subsurface warmth to fuel periodic electromagnetic tantrums. The most haunting detail emerged when astronomers mapped the signal origins. The bursts weren't emanating randomly, they clustered along a narrow equatorial band, as if something beneath the surface was structurally weaker there. One provocative paper suggested this alignment might hint at tidal forces from a long-ago close encounter with a star or black hole, leaving the comet's interior fractured like a cracked eggshell. Whatever the truth, C/2015 ER61 forces us to confront an unsettling reality. The quietest comets might be the loudest storytellers. Their silence isn't emptiness, it's the calm before another electromagnetic scream echoes across the solar system, reminding us just how little we know about the dark hearts of these cosmic travelers. C/2022 didn't just emit radio noise, it composed with it. When astronomers first tuned into this interstellar wanderer, they expected the usual chaotic static of solar wind interacting with cometary gases. Instead, they found something that made them double-check their instruments, a series of harmonic frequencies so precise they resembled the output of a carefully calibrated transmitter. The signals weren't random. They followed mathematical ratios with primary tones at 1.1 GHz accompanied by secondary frequencies at exact integer multiples, like the harmonic overtones of a musical instrument. The discovery ignited immediate debate. Natural cosmic radio emissions rarely exhibit such orderly structure. One camp argued for an exotic form of plasma resonance, where charged particles in the comet's ionized gas cloud vibrated in sync with the solar wind's magnetic oscillations. Simulations suggested that if C/2022 had an unusually uniform coma free of turbulence, its plasma could act like a natural resonator, amplifying specific frequencies while suppressing others. The result, a fleeting but unmistakable harmonic signature, but critics pointed to an eerie detail. The harmonics weren't stationary. They drifted over time, slowly descending in pitch as the comet rotated, as if some unseen force was tuning them like a cosmic dial. This behavior defied most known natural processes, leading to more speculative theories. Could the comet's nucleus contain crystalline structures, perhaps layers of aligned minerals, that vibrated mechanically under solar heating, generating these coordinated frequencies? Or might its interstellar journey have left it cloaked in a shell of exotic ices that conducted electromagnetic waves in unexpected ways? The most provocative hypothesis came from an unexpected corner: acoustic engineers. They noted the harmonic spacing matched patterns seen in cavity resonance, where waves bounce between reflective surfaces. If C/2022 harbored subsurface caverns or fissures of just the right geometry, sunlight-induced pressure waves inside them might generate these radio harmonics indirectly. One paper even suggested the comet could act like a colossal, tumbling flute, with solar wind whistling through its pores to produce ethereal electromagnetic notes. Yet for all the natural explanations, one observation lingered uncomfortably. The harmonics occasionally locked into perfect ratios for minutes at a time, intervals far longer than typical plasma fluctuations. Statistical analysis showed these stable periods were improbable by random chance alone, reviving whispers of the unthinkable. Could something be modulating the signals? The scientific community swiftly dismissed deliberate origins, but the anomaly forced a humbling admission. However mundane the truth might be, our current physics can't fully explain why this particular comet sang with such eerie precision. As C/2022 receded, its final transmission offered poetic symmetry. The harmonics didn't fade into noise, they unraveled note by note, the higher frequencies vanishing first until only the deepest tone remained. Then silence, whether a quirk of chemistry or a glimpse of undiscovered physics. This comet's song remains a haunting reminder that the universe often speaks in patterns we're only beginning to decipher. And sometimes the most profound mysteries don't come as shouts or screams, but as a whisper in perfect pitch. C/2013 US 10 should have been just another cosmic snowball, but it left behind something impossible. Long after this interstellar traveler whipped past the sun and vanished into deep space, radio telescopes kept picking up faint echoes of its presence. These weren't ordinary reflections bouncing off the comet's retreating dust trail. They were delayed signals arriving hours, sometimes days after the initial transmissions, as if the void itself was reluctant to let go of this visitor's electromagnetic fingerprint. At first, researchers assumed instrument glitches. Space is full of noise and false echoes aren't unheard of. But when multiple observatories from Arecibo to Parkes recorded identical lingering pulses, the reality set in. US-10's radio signature was persisting in ways physics couldn't readily explain. The leading theory points to an invisible wake of ultra-fine cosmic dust, finer than cigarette smoke, left in the comet's path. As radio waves from Earth struck these microscopic particles, they might have scattered unpredictably, ricocheting through the cloud like pinballs before eventually looping back to our receivers. But the numbers didn't add up. Even the finest dust should have dispersed within hours, not days. That's when astronomers turned to a wilder idea. What if the comet's chemical composition had temporarily altered the fabric of space around it? Spectroscopy revealed US-10 was spewing unusual carbon chain molecules, the kind that can become ionized and twist local magnetic fields. In this scenario, the comet's emissions might have briefly created a natural echo chamber, warping spacetime just enough to trap and delay radio waves like sound bouncing through a canyon. Then came the clincher. Deep archival analysis showed similar delayed echoes had been detected before, but always dismissed as equipment quirks. Now, with US-10's ghostly afterglow confirmed, researchers are revisiting decades of data, wondering how many other interstellar visitors whispered back to us long after they'd gone. Whether through exotic chemistry or undiscovered physics, this comet's farewell was anything but silent. It was a reminder that some cosmic conversations don't end when the speaker leaves the room. They linger, fading slowly, like a question hanging in the dark. Comet C/2017 K2 didn't just send signals, it teased them. Unlike the steady pulses or rhythmic bursts of other interstellar visitors, this one played by its own rules, flickering in and out of detectability like a cosmic light switch stuck between settings. One day, radio telescopes would catch a blazing surge of emissions at 1.4 GHz, strong enough to drown out background static. The next, silence so absolute, researchers triple-checked their equipment, convinced they'd lost the signal entirely. This wasn't just irregular, it was strategic, as if the comet had a built-in dimmer switch no one could explain. The mystery deepened when astronomers noticed a chilling pattern. The signals didn't vanish randomly. They disappeared precisely when K2 rotated a specific face away from the sun, suggesting something on its dark side was killing the emissions. Normally, comets glow brightest when heated by sunlight, but K2 did the opposite. Its signals thrived in shadow, then choked in direct light. This backward behavior led to a radical theory. The comet's surface might be riddled with cold traps, deep crevices where volatile ices could stay frozen even under solar bombardment. When sunlight hit these shadowed pockets just right, trapped gases might explosively sublimate, creating temporary plasma clouds that amplified radio waves. But when that same face turned fully toward the sun, the heat could overwhelm the process, vaporizing the ices too quickly for coherent signals to form. Then came the real head-scratcher. During one particularly long quiet phase, the Green Bank telescope detected something no one expected. Ultra-weak, low-frequency hums beneath the noise floor, as if the comet was whispering when everyone thought it was mute. These faint vibrations matched the resonant frequency of water molecules, but at intensities 1,000 times weaker than any known cometary emission. Some researchers proposed that K2's interior might harbor liquid water pockets, kept from freezing by salt or ammonia acting as antifreeze. As the comet twisted in sunlight, these hidden aquifers could slosh against their icy walls, generating barely detectable tremors that rippled up through the crust. The most haunting detail emerged when scientists mapped the signal outages. The blackouts weren't random. They followed a cycle aligning with the comet's distance from the sun. Whenever K2 crossed an invisible threshold roughly 200 million miles from our star, its radio voice cut out completely, only rebooting once it retreated. This dead zone had no precedent in comet science, hinting that some critical physical process, perhaps the breakdown of a specific type of ice or the activation of an unknown magnetic interaction, only functioned within a narrow cosmic sweet spot. By the time K2 drifted beyond observation range, it left behind more questions than answers. Was this intermittent broadcast just a quirk of chemistry or evidence of a far stranger mechanic at work? One thing's certain, this comet didn't just defy expectations. It rewrote the rules of how interstellar objects communicate, one cryptic, on-again, off-again transmission at a time. And somewhere in those silent gaps between signals, the universe might have been whispering secrets we're only beginning to suspect. When Comet C/2023H1 swung through our inner solar system, it didn't just bring icy debris from another star, it brought a cipher. As radio telescopes locked onto its faint glow, they captured something that sent spectral analysts into a frenzy: emission lines that shouldn't exist. These weren't the usual fingerprints of hydrogen, carbon monoxide, or other common cometary volatiles. They were spectral ghosts, sharp, unidentified spikes at wavelengths that matched no known element or molecule in our databases. The anomalies clustered around 2 points, 735 MHz and 1.22 GHz, frequencies typically quiet in cosmic objects. At first, researchers assumed calibration errors may be a glitch in the instruments or interference from terrestrial sources. But when observatories from Chile to Australia independently recorded the same rogue lines, the reality set in. Whatever was generating these signals, it wasn't human-made, and it wasn't anything we'd catalogued before. Theories ricocheted through scientific circles. One group proposed exotic molecular transitions. Perhaps the comet carried ices forged in environments so alien, their quantum behaviors defied Earth-based chemistry. Labs scrambled to recreate extreme cold, low-density conditions mimicking interstellar space, bombarding rare ice mixtures with radiation to see if they could reproduce the spectral lines. No luck, another camp pointed to plasma physics, suggesting that charged particles in H1's coma might be colliding in ways that generated temporary, unstable compounds, emitting brief but detectable frequencies. Then came the curveball. A reanalysis of old data from the Rosetta mission revealed something startling: faint, previously dismissed blips at similar wavelengths in Comet's 67P's emissions. At the time, they'd been written off as noise. Now, with H1's stronger signals as a reference, astronomers wondered, had we been overlooking these spectral oddities all along? The implications were staggering. If these lines weren't flukes but signatures of some widespread but overlooked cosmic process, it would mean our understanding of interstellar chemistry had gaping holes. The most haunting detail emerged when researchers noticed the lines weren't static. They drifted slightly over time, as if whatever produced them was degrading or transforming under sunlight. By the time H1 retreated beyond observational range, the mystery lines had faded entirely, leaving behind no answers, only a trail of disrupted assumptions. Whether the result of undiscovered physics, exotic materials, or something else entirely, this comet's spectral whispers were a wake-up call. The universe, it seems, still holds elements or interactions we've yet to even name. And with each new interstellar visitor, we're reminded how much of the cosmic periodic table might still be waiting in the dark. Comet C/2019 Y4 didn't just emit radio waves, it twisted them. When astronomers first analyzed its signals, they stumbled upon something extraordinary. The emissions weren't just random noise. They were polarized, their electromagnetic waves aligned in a way that defied everything we know about natural cosmic radio sources. This wasn't just an anomaly, it was a cosmic fingerprint, a signature so rare in natural objects that it sent researchers scrambling for explanations. Polarization in space usually comes from strong magnetic fields, like those around pulsars or the swirling disks of black holes. But a lone comet, these icy wanderers aren't exactly known for generating organized electromagnetic forces. Yet there it was, clear as day in the data, a distinct, measurable alignment in the radio waves streaming from Y4's nucleus. The polarization wasn't constant either. It shifted as the comet rotated, as if some hidden structure beneath its surface was methodically rearranging the signals like a cosmic kaleidoscope. One theory points to an unusually metallic core. If Y4's interior was laced with iron-rich minerals, sunlight could have heated these conductive materials unevenly, creating localized magnetic hotspots. As the comet spun, these regions might have acted like primitive radio antennas, imprinting order onto the chaotic emissions rising from its surface. Another, more radical idea suggests the polarization came not from the comet itself, but from its journey. Interstellar space is threaded with faint magnetic fields, and if Y4 had spent eons drifting through a particularly strong region, its dust and ice particles could have aligned like microscopic compass needles, preserving that magnetic memory even as it entered our solar system. Then came the clincher, a detail that made the mystery even deeper. The polarization didn't match any known pattern. Instead of the smooth, predictable shift seen in magnetized plasmas, Y4's signals jittered, flipping alignment abruptly at irregular intervals. It was as if something inside the comet was intermittently scrambling the signals, adding an extra layer of encryption to its already puzzling transmissions. Some researchers wonder if this erratic behavior hints at an internal structure unlike anything in our solar system, perhaps layers of exotic ices cracking under thermal stress, or pockets of superconducting materials reacting unpredictably to sunlight. What makes Y4's polarized whispers so haunting isn't just their strangeness, it's the lingering question they leave behind. If a single comet from the depths of interstellar space can warp electromagnetic waves so dramatically, what else might be out there, silently twisting the fabric of radio signals as they pass? The universe, it seems, has more ways of communicating than we've ever imagined, and sometimes it speaks in a language we're only beginning to decode. Comet C/2018 C2 was cruising silently through the solar system when, without warning, it screamed. For months, this interstellar visitor had emitted nothing more than faint radio static, barely detectable even with our most sensitive instruments. Then, during a routine observation window, its signal strength skyrocketed by a factor of 10,000 in less than 12 hours. It was like watching a candle suddenly explode into a supernova. The surge centered around 800 MHz, a frequency typically associated with charged particle interactions, but the intensity was off the chart, equivalent to a solar flare erupting from an object no larger than a city block. And just as suddenly as it began, the outburst ceased, leaving astronomers with a single burning question: what on Earth, or rather beyond Earth, had just happened? The leading natural explanation points to an extreme version of cometary outbursts, where trapped gases beneath the surface rupture through weakened crust. But C2's flare defied all known precedents. Local comets like 29P Schwarzmann-Wachmann occasionally experience violent eruptions, yet none have ever produced radio emissions this powerful. Theorists suggest the comet might have been packed with supervolatile ices like solid nitrogen or carbon monoxide materials that vaporize explosively when exposed to sunlight. If a pocket of these ices suddenly breached the surface, the resulting gas jet could have ionized into an enormous temporary antenna, amplifying ambient solar radiation into that staggering signal spike. Yet skeptics note an eerie detail in the timing. The surge peaked precisely when C2 crossed an invisible boundary in Earth's magnetosphere called the magnetopause, the point where our planet's magnetic field meets the onslaught of solar wind. Coincidence, maybe, but some researchers speculate the comet's own faint magnetic properties, combined with this high-energy environment, triggered an unforeseen resonance effect. Imagine a cosmic feedback loop, solar particles energizing the comet's plasma, which then interacts with Earth's magnetic field, creating a self-reinforcing electromagnetic storm. The most haunting possibility emerged from spectral analysis. Hidden within the signal surge were faint but detectable harmonics, subsidiary frequencies mirroring the main burst at precise mathematical intervals. This isn't unheard of in natural phenomena, but the symmetry was too perfect. One controversial paper suggested the pattern resembled artificially amplified signals, where harmonics are deliberately enhanced for clearer transmission. The scientific community largely dismissed this as pareidolia, the human tendency to find patterns in randomness, but the implication lingers like static in the air. Whatever caused C2's electrifying performance, its finale was just as enigmatic. Instead of fading gradually, the signals terminated abruptly, as if someone had flipped a switch. Subsequent observations found the comet's surface pockmarked with fresh scars, evidence of a catastrophic structural failure. Whether a natural pressure release or something more exotic, this interstellar visitor left us with a masterclass in cosmic ambiguity. Some mysteries don't whisper clues, they roar them, then vanish before we can decipher the message. And in that brief, blazing moment, C/2018 C2 reminded us how much violence can hide beneath the icy silence of the cosmos. The signals from Comet C/2020 R4 weren't just unusual, they were unnervingly familiar. As radio telescopes locked onto this interstellar visitor, they detected a sequence of pulses so structured, so deliberate, they sent a ripple of disbelief through the astronomical community. The pattern was unmistakable, short bursts followed by longer tones, clustered in groups that bore an eerie resemblance to Morse code. It wasn't just random noise, it was a cadence, a rhythm, as if the comet itself was tapping out a message from the void. At the heart of the mystery was the signal's precision. Natural cosmic radio emissions rarely maintain such consistent timing, yet R4's pulses held their intervals with near-mechanical accuracy. The dots lasted precisely 0.3 seconds, while the dashes stretched to 0.9, separated by clean, uniform gaps. When researchers fed the pattern into decoding software, the output was chaotic. No intelligible language or mathematical sequence emerged. But the mere fact that it could be fed into a decoder at all was enough to ignite fierce debate. The scientific community scrambled for natural explanations. One theory pointed to an unusually rigid internal structure, perhaps a fractured nucleus with deep, resonant chambers. As solar heating caused gas to escape through specific fissures, the vibrations might have produced rhythmic pressure waves, converting the comet into a natural radio transmitter. Others suggested a more exotic possibility: magnetized plasma rings. If R4 carried remnants of its birth system's magnetic fields trapped in superconducting ices, solar-wind interactions could have generated pulsating currents, shaping the emissions into those cryptic bursts. Yet for all the plausible theories, one observation refused to fit neatly into any model. The signal's modulation wasn't entirely random. Over weeks of observation, astronomers noticed subtle drifts in the pulse lengths, not chaotic fluctuations, but gradual, almost deliberate adjustments, as if the sender was fine-tuning its broadcast. Statistical analysis revealed the changes followed a weak but detectable logarithmic pattern, a hallmark of certain natural oscillating systems, from pulsars to seismic tremors. But in a comet that was unprecedented, the most tantalizing and controversial clue came from archival data. When researchers compared R4's signal to old recordings of deep space radio anomalies, they found a handful of uncanny matches, fleeting bursts from the 1970s and 80s with similar dash and dot structures, all dismissed as interference at the time. Could these have been earlier visits from interstellar objects like R4, their signals overlooked or misinterpreted? The implications were staggering. If true, it would suggest such patterned emissions aren't flukes, but a recurring feature of certain cosmic wanderers, a hidden language of the universe we're only now beginning to hear. By the time R4 faded from detection, it left behind more than just data. It challenged the very boundary between natural phenomenon and something more enigmatic. Whether a quirk of physics or a cosmic coincidence, this comet's Morse-like whispers remind us that the universe often blurs the line between randomness and design. And while we may never know if those pulses carried meaning, their mere existence proves one thing: sometimes the cosmos doesn't just speak, it punctuates. Comet C/2017 T2 didn't just broadcast signals, it wandered. Unlike the steady tones of most cosmic radio sources, this interstellar visitor's emissions had a peculiar habit of sliding up and down the frequency spectrum, drifting like a radio dial slowly turning itself. These weren't random fluctuations. The shifts followed a smooth, almost deliberate curve, dropping nearly 1 megahertz over the course of a week before reversing direction and climbing back up. To astronomers, this behavior was more than unusual, it was borderline unnatural. Frequency drift is a hallmark of human-made satellites, their signals Doppler shifting as they move relative to Earth. But in a natural object, that was a puzzle with no obvious solution. The mystery deepened when researchers tracked the drift's pattern. Instead of aligning neatly with the comet's rotation or orbit, the frequency shifts correlated most strongly with solar activity. Whenever solar flares or coronal mass ejections bombarded T2, its signals would begin their spectral slide, as if the comet's plasma environment was recalibrating itself in real time. One theory suggests the comet's nucleus might be wrapped in a shroud of hypervolatile ices materials so sensitive to heat that even minor solar gusts could trigger explosive sublimation. As these gases erupted, they'd temporarily alter the density and electrical properties of T2's coma, effectively tuning its radio emissions like a cosmic synthesizer. But critics pointed to an unsettling detail. The drift rate wasn't perfectly chaotic. Hidden within the data was a faint but detectable periodicity, a 67-hour cycle where the frequency would bottom out before rising again, regardless of solar input. This rhythmic behavior hinted at something deeper. Perhaps the comet's internal structure itself was resonating, its hidden chambers of ice and dust vibrating at frequencies that subtly modulated the escaping radio waves. Imagine a colossal, tumbling flute, its hollow interior whistling electromagnetic notes as sunlight heated and cooled its walls. The most provocative clue came from an unexpected comparison. When researchers analyzed decades of satellite telemetry, they found something uncanny. T2's drift pattern bore an eerie resemblance to old Soviet-era relay satellites, their signals warped by spinning stabilizers. Of course, no one was seriously suggesting this comet was some derelict spacecraft. But the similarity raised a profound question. Could natural processes inadvertently mimic the signatures of technology? If so, how many other cosmic signals have we dismissed as artificial when they were just nature's way of playing tricks on our expectations? By the time T2 retreated into the outer solar system, its drifting signals had left an indelible mark on astronomy. What began as a curious anomaly became a case study in cosmic ambiguity, a reminder that the universe often blurs the line between the engineered and the elemental. Whether a quirk of chemistry or a glimpse of physics we've yet to name, this comet's spectral wanderings challenge us to listen more carefully, to question our assumptions, and to embrace the possibility that sometimes the most ordinary-looking objects can broadcast the most extraordinary secrets. And somewhere in that slow, meandering frequency drift, there might just be a new language of the cosmos waiting to be decoded. Amidst the symphony of bizarre signals from interstellar visitors, Comet C/2016 U1 stood out for its eerie silence. Classified as one of the largest known interstellar objects to pass through our solar system, its sheer size estimates suggested a nucleus over 10 miles wide should have made it a beacon of radio emissions. Instead, telescopes detected barely a whisper from this cosmic giant, defying every expectation. This wasn't just a quiet comet, it was a cosmic stealth bomber, gliding through the solar system without leaving the usual electromagnetic breadcrumbs. The mystery only deepened when spectral analysis revealed U1's surface was anything but inert. Scans showed patches of carbon dioxide and methanol ice, volatiles that typically erupt into vibrant gas jets when exposed to sunlight. Yet somehow this comet resisted the usual theatrics. One theory points to an unusually thick, insulating crust, perhaps a layer of organic rich tar or porous, charcoal-like material that sealed its ices beneath an almost hermetic barrier. Imagine a comet wrapped in a cosmic pressure suit, its volatile gases trapped so tightly that even the sun's heat couldn't pry them loose. Without outgassing, there'd be no plasma, no charged particles, just radio silence. But there's a catch. When astronomers examined U1's trajectory, they noticed something peculiar. Its path bore subtle deviations, slight wobbles that hinted at some outgassing occurring invisibly. This raised a spine-tingling possibility. What if the comet wasn't silent because it was dormant, but because its emissions were literally invisible to our instruments? Some researchers speculate U1's gases might have been dominated by nitrogen or pure oxygen, molecules that don't produce strong radio signatures when they ionize. Or perhaps its outgassing was so diffuse, so spread across its vast surface, that it never concentrated enough to generate detectable bursts. The most haunting clue came from its darkness. U1 reflected less than 3% of incoming sunlight, making it one of the blackest natural objects ever observed. This extreme albedo suggested a surface unlike anything in our solar system, possibly coated in exotic carbon compounds forged in the radiation-heavy environment near another star. If true, this comet's silence wasn't a fluke. It was a fingerprint of its alien origins, a testament to how differently chemistry might play out around distant suns. What lingers isn't just the puzzle of U1's quiet, but what it implies about the cosmos. For every interstellar visitor that screams its presence with bizarre signals, there might be a dozen silent giants slipping past unnoticed. These stealthy wanderers could be carrying entire libraries of untold cosmic history in their icy cores, if only we knew how to listen. And that realization forces a humbling question. How much of the universe's story remains unheard, simply because we've been tuning our instruments to the wrong frequency? Comet C/2021 G1 didn't just send signals, it reflected them. When astronomers first tuned into this interstellar visitor, they expected the usual chaotic bursts of radio noise. Instead, they stumbled upon something that made them question their instruments. A sequence of pulses so precise, so unnervingly symmetrical, it was as if the comet was echoing itself in reverse. The pattern was impossible to ignore. A string of frequencies would play out, followed by the exact same sequence backward, like a cosmic palindrome etched into static. These mirror signals clustered around 900 MHz, a frequency often linked to plasma oscillations, but their structure defied all known natural processes. Normally, cometary emissions are as disordered as static on a detuned radio, yet here was a transmission with near-perfect symmetry, as if some invisible hand had folded the signal in half. The implications were staggering. Either we'd stumbled upon a previously unknown astrophysical phenomenon, or we were witnessing something far stranger. Theories flared up immediately. Some researchers pointed to an exotic form of wave bouncing, where radio emissions from one side of the comet's nucleus might reflect off an unusually dense ionized gas cloud, creating a delayed, reversed copy. Others proposed a more unsettling idea, that G1's internal structure contained some form of resonant cavity, perhaps a network of subsurface fractures or ice chambers acting like a natural echo chamber for electromagnetic waves. Imagine sunlight energizing the comet's surface, sending vibrations through hidden tunnels of ice, only for those vibrations to rebound in perfect reverse order. Yet skeptics noted an eerie detail. The mirrored sequences weren't just rough imitations, they were mathematically precise, with timing differences measured in microseconds. This level of symmetry is vanishingly rare in nature, leading a minority of theorists to float a radical hypothesis: could the signals be engineered? Not necessarily by intelligence, but by some naturally occurring structure like a crystalline matrix within the comet, acting as a passive amplifier and inverter of ambient radiation. The idea wasn't entirely far-fetched. Certain mineral formations on Earth, like quartz, can manipulate electromagnetic waves in surprising ways. If G1 carried alien analogs of these materials, who knows what kind of radio hall of mirrors it might create? The most tantalizing clue came when researchers mapped the signal origins. The forward and reversed sequences didn't emanate from the same location. Instead, they appeared to originate from opposite hemispheres of the comet, as if something beneath its surface was coordinating this electromagnetic dance. One team suggested that G1 might be a contact binary, two smaller bodies fused together, each with distinct conductive properties that somehow flipped the signals as they passed between them. By the time G1 vanished into the depths of space, it left behind more than just questions. It redefined what we thought possible. Whether a quirk of physics or a glimpse of cosmic artistry, this comet's mirrored whispers challenge us to reconsider the boundary between randomness and design. After all, in a universe of infinite possibilities, even echoes might have something new to say. The strangest thing about Comet C/2019 E3 wasn't what it emitted, it was what it left behind. Long after this interstellar visitor had vanished from telescopic view, radio observatories kept detecting faint bursts of energy exactly where the comet's trajectory should have carried it. These weren't random blips in the cosmic static. They clustered around the same frequencies E3 had emitted during its close approach, as if some invisible remnant of the comet was still drifting through space, whispering long after its nucleus had faded into darkness. At first, researchers dismissed the anomalies as instrumental artifacts, ghost signals created by Earth's own atmosphere or interference from passing satellites. But when the Green Bank Telescope and the Allen Telescope Array independently confirmed the same phantom emissions, tracing them back to the comet's projected path months after its departure, the astronomy community had to confront a spine-tingling possibility. E3 might have left something invisible in its wake. The leading theory points to an ethereal trail of ultra-fine dust, so diffuse it doesn't reflect sunlight but dense enough to interact with cosmic radiation. As charged particles from the solar wind collide with these microscopic remnants, they could generate fleeting radio pulses, a faint electromagnetic echo of the comet's passage. But there's a catch: the signals weren't uniform. They spiked at irregular intervals, mimicking the same erratic pattern E3 had exhibited when it was still observable. This level of consistency suggests something far more structured than random debris. One radical paper proposed the comet had shed not just dust but magnetized filaments, thread-like structures of ionized gas frozen into bizarre configurations by the deep cold of interstellar space. These filaments, if they existed, might act like cosmic antennae, resonating with ambient radiation to recreate the comet's original emissions long after its nucleus had moved on. It's a controversial idea, but not without precedent. Similar phenomena have been observed in the wakes of some active galaxies, where magnetic hair stretches for light years behind supermassive black holes. The most haunting detail emerged when astronomers noticed the phantom signals weren't fading uniformly. Instead, they pulsed, sometimes vanishing for weeks before reappearing slightly shifted in frequency, as if whatever was generating them was slowly unraveling in the void. By the time the last whispers were detected nearly a year after E3's departure, they drifted almost 2 MHz downward, like a recording played at ever-slowing speed. Whether caused by exotic physics or something we've yet to imagine, these phantom signals force us to reconsider what it means for a comet to truly leave our solar system. Some travelers, it seems, don't just pass through space, they etch their presence into it, leaving behind electromagnetic footprints that linger like cosmic afterthoughts. And if E3's ghostly encore teaches us anything, it's that the universe rarely says goodbye without whispering one last cryptic farewell. When Comet C/2022 F1 first began transmitting signals, astronomers almost dismissed them as background noise, just another blip in the cosmic static. But upon closer inspection, they stumbled upon something that made quantum physicists lean forward in their chairs. Embedded within the usual hiss of cometary radio emissions was a pattern of fluctuations so precise, so mathematically crisp, it mirrored the behavior of particles at the quantum scale. These weren't random fluctuations, they followed the statistical signatures of quantum noise, the same subtle jitter that governs the behavior of subatomic particles. To detect this at a macroscopic level, emanating from an object millions of miles away, was like hearing the universe whisper its deepest secrets through a comet's static. The signals clustered around 1.6 GHz, but it wasn't their frequency that shocked researchers, it was their texture. When analyzed with quantum-level precision, the wave patterns exhibited minute, randomized jumps in phase and amplitude, indistinguishable from the shot noise seen in entangled photon experiments. Natural cosmic radio sources don't behave this way. Solar flares, pulsars, even the chaotic emissions of black holes all produce noise that follows classical physics. F1's signals, however, danced on the edge between order and quantum chaos, as if the comet itself was a cosmic-scale laboratory demonstrating principles we've only observed in controlled experiments on Earth. Theories erupted like solar flares. One camp argued for an exotic form of quantum tunneling in the comet's ices. Perhaps its nucleus contained ultra-cold superconductors or Bose-Einstein condensates, materials that only form under extreme conditions. If sunlight excited these structures, they might vibrate at quantum frequencies, imprinting their behavior onto the comet's radio emissions. Others pointed to a more radical idea. F1's journey through interstellar space could have left it peppered with atomic-scale defects, creating a labyrinth of tiny tunnels in its ice where particles behaved like waves, interfering with each other to produce this eerie statistical signature. Then came the controversy. A small but vocal group of researchers noted the noise patterns bore an uncanny resemblance to theoretical models of decoherence, the process by which quantum systems lose their weirdness and collapse into classical states. In human-made quantum computers, engineers fight decoherence with shielding and error correction. Yet here was a natural object apparently exhibiting it in the wild. Could F1's nucleus be acting like a crude, planet-sized quantum computer, its icy matrix hosting spontaneous quantum processes that leaked into its emissions? Mainstream astronomers balked at the comparison, but the data refused to be ignored. The most haunting detail emerged when researchers compared F1's signals to deep space anomalies logged over decades. Buried in old SETI archives were a handful of recordings with similar quantum statistical profiles, all dismissed as equipment glitches. Now, with F1 as a reference, those anomalies took on new significance. Were they glimpses of a larger, overlooked phenomenon, a hidden language of quantum noise woven into the fabric of the cosmos, broadcast not by civilizations, but by the icy wanderers drifting between stars? By the time F1 retreated beyond observational range, it left behind more than just data. It forced us to confront the possibility that quantum weirdness isn't confined to labs or futuristic technology. It might be etched into the very ices of the cosmos, humming softly in the dark. And if that's true, then every comet silently tumbling through space could be carrying not just ice and dust, but fragments of a quantum universe we're only beginning to hear. Comet C/2018 F4 didn't just emit signals, it composed them. When radio telescopes first tuned into this interstellar visitor, researchers expected the usual chaotic static of solar wind colliding with cometary gases. Instead, they discovered something that defied all expectations, a cascading array of frequencies layered atop one another, rising and falling in what could only be described as a cosmic symphony. The emissions weren't random noise. They were structured, almost orchestrated, with distinct high, middle, and low-frequency components interacting in ways that mirrored the harmonic complexity of a musical masterpiece. At the heart of the mystery was the signal's unprecedented richness. Most comets broadcast on a single dominant frequency, perhaps with faint harmonics. But F4's transmissions spanned nearly 30 separate bands simultaneously, from deep, resonant ultra-low frequencies to piercing high-frequency whistles. These weren't independent channels, they fluctuated in tandem, their amplitudes rising and falling in delicate counterpoint, as if some unseen conductor were balancing their volumes. Analysis revealed the pattern wasn't static either. Over days, the composition evolved, with certain frequencies fading as others swelled to prominence, creating an ever-shifting auditory tapestry that left astronomers torn between awe and bewilderment. Theories about this symphony split the scientific community. One faction argued for an extreme version of plasma resonance. If F4's coma contained dense, stratified layers of ionized gas, each vibrating at its own natural frequency, solar wind could have energized them like bows drawn across cosmic strings. Simulations showed that under perfect conditions, such a system might produce overlapping harmonic oscillations, though none could replicate the breathtaking complexity of F4's emissions. Skeptics countered that no known comet, even those from interstellar space, carries enough plasma to generate such a multilayered signal. Another camp pointed to the comet's bizarre rotation. Unlike most space rocks that tumble chaotically, F4 spun with eerie precision around two axes simultaneously, a phenomenon called biaxial rotation. This double spin could have created intricate patterns in outgassing, with jets erupting in rhythmic sequences that amplified specific frequencies at specific times. Picture a frozen ballerina pirouetting through space, her icy dress shedding harmonic ripples with every turn. Yet the most haunting possibility emerged from spectral analysis. Hidden within F4's radio symphony were faint but detectable beat frequencies, ghostly interference patterns created when two closely spaced tones interact. These beats didn't match any known solar or planetary influence. Instead, they hinted at something far stranger. The comet's nucleus itself might be vibrating, its internal structure resonating like a colossal tuning fork. If true, F4 wasn't just singing. It was trembling, its entire form humming at frequencies that echoed through its electromagnetic emissions. By the time the comet retreated beyond observational range, its final act only deepened the enigma. The symphony didn't fade gradually into silence. It unraveled, higher frequencies vanishing first until only the deepest bass tones remained, a cosmic diminuendo that left astronomers questioning whether they'd witnessed a fluke of physics or glimpsed something more profound. Perhaps what we call chaos and harmony are just two sides of the same celestial coin, and comets like F4 are the universe's way of reminding us that even in the void, there's music waiting to be heard if only we learn how to listen. Comet C/2023 D1 didn't just push the boundaries of what we know, it erased them entirely. Among the 25 unexplained signals from interstellar visitors, this recent traveler stands out as the most confounding, leaving astronomers with more questions than answers. From the moment it entered our solar system, D1 broadcast signals that defied every classification system, patterns so alien they seem to mock our attempts to understand them. The first anomaly appeared in its frequency shifts. Unlike other comets that drift gradually or pulse erratically, D1's emissions jumped, hopping unpredictably between discrete frequencies like a cosmic radio station with a broken dial. One moment it would broadcast at 800 MHz, the next it would leap to 1.4 GHz without transition, as if an invisible hand were flipping a switch. Even more bizarre, these jumps weren't random. Hidden in the chaos was a fractal pattern, repetitions of smaller frequency clusters nested within larger ones, like a set of matryoshka dolls carved from static. Then came the polarization mystery. Most comets emit radio waves that scatter in all directions, but D1's signals arrived with a twisted, corkscrew-like alignment, spiraling through space in a way that suggested extreme magnetic turbulence. Yet spectral analysis revealed no unusual magnetic fields around the comet. Instead, researchers began to suspect its dust was the culprit. Spectroscopy showed D1's coma was laced with microscopic, needle-shaped metallic particles, possibly iron or chromium, that could theoretically polarize emissions as they tumbled in sunlight. But simulations couldn't replicate the signal's intensity, leaving a gaping hole in the explanation. The most unsettling feature, though, was the timing. For 72 hours straight, D1 emitted pulses spaced exactly 11 minutes apart, a precision unheard of in natural cosmic objects. The intervals were so consistent, the margin of error was less than a millisecond. Astrophysicists scrambled to find a mechanism. Could the comet's rotation be synchronized with some hidden internal oscillator? Or was there a resonant structure beneath its surface, vibrating like a quartz crystal in a cosmic wristwatch? The debate grew even hotter when someone noticed an eerie coincidence. 11 minutes is the average time between solar wind pressure fluctuations at Earth's orbit. Was D1 somehow tuned to our sun's rhythm despite originating from another star? By the time D1 retreated beyond observational range, it left behind one final enigma. The signals didn't just fade, they unraveled, the fractal patterns disintegrating into noise before vanishing entirely, as if whatever process generated them had exhausted itself. Whether a natural phenomenon beyond our current physics or something even more extraordinary, this comet's transmissions remain a haunting reminder that the universe's strangest messengers might not just be passing through, they might be redefining reality as they go. These 25 unexplained signals from interstellar comets don't just defy our expectations, they rewrite the rules entirely. From Oumuamua's eerie Morse-like pulses to C/2023 D1's fractal frequency jumps, each one shatters the notion that comets are simple, silent snowballs drifting through space. Instead, they appear as cosmic enigmas, broadcasting signals that range from harmonic symphonies to quantum static, from polarized whispers to phantom echoes that linger long after the comet itself has vanished. The sheer variety alone is staggering. Some signals pulse with rhythm, others drift like out-of-tune radios, and a few even mimic patterns so structured they border on the artificial. What binds them together is the profound challenge they pose to science. If natural processes alone can produce emissions this bizarre, then our understanding of physics is riddled with gaps. How does a comet's icy core generate quantum noise? What unknown chemistry twists radio waves into perfect spirals of polarization? Could some of these signals be the result of materials or magnetic phenomena we've never encountered in our own solar system? The implications stretch far beyond comets themselves. They hint at an interstellar environment far stranger, far more complex than we've dared to imagine. But the most electrifying question isn't just how these signals form, it's why. Are they accidental byproducts of cosmic chaos, or could they serve a purpose we can't yet grasp? For astrobiology, the possibilities are tantalizing. If a comet's internal structure can act as a natural radio transmitter, could similar processes occur on icy moons or rogue planets, creating detectable techno-signatures without any intelligence behind them? Conversely, if even a fraction of these signals resist natural explanation, could we be overlooking something monumental? The line between anomaly and artifact is thinner than we think. For now, the truth remains just out of reach, drifting like these comets themselves through the unknown. But every new interstellar visitor brings fresh clues, and every unexplained signal is another piece of a puzzle we're only beginning to assemble. So what do you think these cosmic messages mean? Are they the static of a universe more intricate than we dreamed, or something even more extraordinary? Share your wildest theories below, because the next time one of these wanderers whispers to us from the dark, it might just change everything. And if you're as captivated by these mysteries as we are, don't forget to follow along, because the universe isn't done